Recording is rolling. So it is Wednesday, November 2nd. I have a lab lined up for you guys today. You guys have this lab page out from the other day. Remember, I gave you guys all these conceptual questions on work and energy. And then on the side, we already did the potential lab a couple days back. Okay, and today we're going to focus on this lab. Give you guys a very convenient lab table here. Okay. So the ball launchers are back. And we're going to figure out what is the spring constant in the spring. Right. So before I walk you guys through that, some other announcements. Picture retakes are this Friday in the gym lobby. So if you don't like your original picture, then wear something good to school on Friday. And before you guys walk out the door today, I will give you guys your next quiz, your energy quiz. So that'll be open notes take home, just like they did so far. And this lab paper might be helpful for notes. So tell you what, this lab page, I'm going to pick up from you guys just sometime before the end of this week. Can you guys just turn this in before the weekend, right? Because it could be useful open notes for this quiz, right? And this quiz will be due on Monday, right? So you guys have some days to roll out. Right? We still got a couple of book comps to do, but we'll save that for tomorrow. Right? All right, so we're going to focus on this lab today. It's lab today. Right. So your target question is, what is the spring constant in the spring that's gonna blast the ball out, right? So that's the target question. Now, to solve that, I mean, one way you could do it, I guess you could use the Hooke's law, F equals kx, to say, well, what force does it take to compress some distance? But we're not going to go with that method. We're going to do it like a conservation of energy method that involves 1/2 kx squared could be the energy stored in the spring. Is that true? 1/2 kx squared, right? Now, going forward in time, which is going to be the reverse of how we're going to solve it, right? But chronologically, right? You're going to smash this. Well, actually, you're going to compress it first, right? You guys know that because you guys know there's those squishy balls. So it's kind of a technical point that's going to take you guys a lot of trouble. What are you going to do first? Are you going to put the squishy ball in and then smash this in so the ball gets stuck? Or are you going to compress it first and put the ball in after? What are you guys doing? Yeah, compress it first and then put the ball in after. Right. So remember that there's going to be like some number of clicks this can go. Oh, I compressed that before. Right. So you go like click, 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 right? And then you can pull this thing, pow, and then it'll like it'll launch the ball. Right. So if you go click, click, click. Right. Now, isn't there a bunch of spring potential energy now stored in the spring? Right. So that's called 1/2 kx squared, right? 1/2 kx squared, where k is the spring constant that we're solving for. And x, hey, x is like how far I smashed it. Right. Ooh, probably about that distance right there. Right. I bet you guys can measure that. Right. And then when I launch it, pow, all that energy, well, the first thing it's going to do is turn into kinetic energy, like 1/2 mv squared, right? So that'll be a bit, right? So one thing you guys have to know is what is the mass of the ball? And I did leave that detail off the table. So here, so on this table, okay, go ahead and write that in here. Say the mass of the ball. Okay, I grabbed that this morning. Okay. Now, I got 6.4 grams, but don't write 6.4. Yeah, go ahead. This paper? Okay, good. That right here. Right. But don't write 6.4 because you need base SI units. Okay, 6.4 grams. How many kilograms is that equal to? 0.0064 kg. Just like that, right? Because kilo is like 1,000. So yeah, that's 6.4 grams, 0.0064 kilograms. 0.0064 kilograms is the number that you're eventually going to use in some calculations, right? Okay. And so this will have been given some blast speed, therefore, right? And then if you know what the blast speed is, isn't it determinable at that point how far it's going to land following some height, right? Now, the height and the distance, the horizontal displacement, those numbers are easy to measure. You can just take a meter stick out there and measure how many meters it goes, right? Therefore, the way we're going to solve this is exactly backwards of the whole story I just told you. I told you the story chronologically. First, the spring compressed, then it gives the ball speed, then the ball lands some distance, turns into projectile, okay? But we're going to solve this backwards, right? Starting from where the ball lands, okay? Right. So I will take you guys through, here's the way I made this. I'll take you guys through the thought process, like force for the trees using this diagram. Then I will say pretty much the same thing going through this table. So you guys look at the two explanations. Then we'll head outside. You guys can get all your data. Then we'll come back and I'll help you guys crunch the data to get this last column, the answer to the question, what is the spring constant of the spring? Right, you guys see that process? Right. All right. So Okay, you're about to see this explanation twice. First, by looking at this page right here. Okay, so this is gonna be like a two-part lab. You guys see part one and part two to remember to solve the question. Okay, so part one is projectile physics, which is it's just essentially a repeat of the projectile lab that you guys did a few weeks back. Right, just to get the blast speed. Right, and part two is going to be the conservation of energy bit. So part one, you need to figure out, well, you need to know how much time that the ball has been falling for. It's going to be one thing you have to figure out. Okay. Right. So the time of fall, is that going to have something to do with how far it falls? Okay. How about this? Suppose you launch a ball out horizontally and you drop a ball just vertically at the same time. Which ball hits the ground first, or do they hit the ground at the same time? Yeah. Same time. Yeah. You guys remember that same time, right? Right. What that means then is that if you know the height of fall, right, you can determine the time of fall. Is that this expression right here? 1/2 GT squared. Okay, you guys remember that? Hey, 1/2 GT squared. Is that like? Oh, is that calculations earlier? Right. Is that the college equation? The college equation? You guys remember that? Walk into a mine shaft. The ball falls for 5 seconds. 5 times 5 times half a 10, about 125 meters deep. How'd you know that, college? That's that one. That's that story, right? Except the difference here is that instead of measuring the time of fall, you guys don't need any stopwatches today. So no stopwatches. Because stopwatch measuring time is not a very accurate way to do it. A much more accurate way to do is to calculate the time based on the height of fall. Right? You guys see that? Right? So you're going to record how tall is that in meters, right? And that number is going to go right here on your table. Right. So you're going to measure. Some of these you're measuring, some of these you're calculating. So you're going to measure the height of fall, right? You guys going to do that? Okay. Oh, and you can sort of like be given the free fall gravity of the planet. Okay. But we can just do this part of the table right here. What number should I write? 9.8 is good, 10 is good. So pick your favorite, either 9.8 or 10. Okay. Okay. So you're going to measure what's the height of fall. Okay. Now, you're going to use that height of fall in conjunction with the gravity of the planet, free fall gravity, to calculate this time of fall. So this is going to be a calculation right here. Is that true? Okay, calculate the time of fall. You guys got that? Okay. How about this horizontal displacement D? Is that going to be, right? Is that something you can measure? Right, measure. Right, so you can definitely measure that. The same measure. Right? And if you know how far it went and how much time, is there enough information there to get the blast speed? Right? Because the blast speed is the horizontal component of velocity, right? It's just going across at some constant speed. It's not accelerating horizontally, right? You guys remember that projectile physics? Right? What's going on vertical, what's going on horizontal, right? All right. So at this point, we know how fast it's been blasted from the blaster, right? You guys got that? Okay, so that's going to be the next column. You're going to calculate how fast was the ball blasted in meters per second. Okay, all good so far? Okay, all right. Now, everything up to this point in the explanation is what you guys already did for the projectile lab, right? That would be the answer to the projectile lab. It's how fast it was blasted. Okay. But here's where we're going to go an extra step. Okay, what we're going to do is we're going to zoom in on just this right here. So I'm going to blow that up. Boom. That looks like this. Cover up this stuff. That's just for my AP kids. Don't worry about that. Okay. And I'm going to say I have an initial point and a final point. Now I'm ignoring this height call because I'm just focused on this. That's my entire universe right here. Right. At some point, the ball was like spring loaded, ready to go. All the energy was stored in the spring. I could call it 1/2 kx squared. Right. And right after it's been blasted, it's leaving that barrel with some speed. I'll call it V blast, right? Which means it has all kinetic energy. Right. Again, like ignore the height. That's my entire universe right there, right? Point A to point B. Right. It's okay. Okay. So I can set up an equation like this, right? Okay. Now at this point, what would you know? Well, you would know the mass of the ball because I just told it to you. I told it's 0.0064 kilograms, so you know that. You would also know the blast speed because you calculated it by this point using projectile physics, right? Right? Show you guys how to do that. That's what this whole part one of this lab is about, right? You guys see that? Guys see that? Okay. Right. Then So you know how much kinetic energy it has leaving the blaster, right? Leaving the blaster. Okay. And where that energy come from? Well, if energy is conserved, it all came from the spring. Okay. So there's one more number you have to measure, and that is what is the spring compression? That's what X is, right? Spring compression. Okay. So over here, under X, well, you guys see above X, I wrote spring compression because X could stand for lots of different things, but in this context, it stands for spring compression. Right. So you're going to measure this. Right. In fact, I sort of just did this with you guys right here. Right. So I went crunch, crunch, crunch. Here it is. Right. So if I put a pencil mark on this thing right here, and I smash this in, let's say do 3 clicks like right there. It goes right to this Velcro bit right here. Okay. So that distance, let's see what that distance is. Actually, let's just go ahead and do this right here. Help you guys out some more. Okay. That looks like 7 centimeters exactly, like 7.0 centimeters. Okay. So if that's 7 centimeters exactly, and that's assuming you want to do all 3 clicks. So if you want to use that number, you have to do all 3 clicks. What number would go here?
0.07.
0.07. Right. 0.07 per meters. Because when you do your calculations, make sure everything's in base SI units. Is that true? Okay. Okay. And then, right now, you have everything in this equation except for K, but that's the question of the lab is what is the spring constant? Right? How stiff is the spring? Okay, you guys got that? Okay. Now, if you do this completely correctly, then a reasonable value for our K that my classes have begun earlier today should be somewhere between 100 and 200 Newton per meter. That should be the correct order of magnitude. Okay, somewhere about between 100 and 200 Newton per meter. Okay. Right. Any questions so far? Any questions? Right. So here's what we do next. We're gonna go outside. You guys are going to get all your lab data. If you do some calculations, that's awesome. We'll come back to the classroom and I'll guide you guys through the calculations to make sure everybody did this right, got this. Right. I'll give you guys some time to work with each other. You might solve it before I show you the answer. Okay. Right. And then this particular paper, if you want to turn it in today, you can just turn it sometime before the weekend, and then I'll just check off, just make sure you guys did this and this. Right. But if you want to hold on to it for a couple days, then I will give you guys your next take-home quiz before the end of class. And this could be helpful for that if you just want to use this for extra notes for the next couple days. Okay. All right, guys. All right. So let's head outside. I'm gonna stop this recording, and we'll come back later.